Okay, so let's start with, with some kind of an introduction to the idea of sharply O-minimal structures. So, format and degree, and we will discuss these notions in two particular O-minimal structures, semi-algebraic structure and Pfaffian structure. So let's start with the semi-algebraic structure. So our alg, I guess. So a semi-algebraic set is going to be a union, finite union, of systems of polynomial equations and also polynomial inequalities, however many. So P, the P's and the Q's are going to be polynomials in, say, L variables, x1 up to xl. And for such a set, there is a format, F, and F, which is the format, in this particular case, it's very simple. It's just equal to L, the ambient dimension of X, right? X is in RL, because all of these equations and inequalities have L variables. And the degree, which for this particular structure is called, is historically called complexity, it's going to be the sum of the degrees of all of these P's and Q's. Okay, and these two numbers control the geometry and topology of X in the following sense. So theorem. So I will not explain what are O-minimal structures and what are O-minimal cells. So I will not explain what are cells, but yesterday they were mentioned. So the theorem goes as follows. Let's say that we have semi-algebraic sets in RL of degree d. So every one of them has degree d. That's what I mean. Then there exists a cellular decomposition of RL. Right, so RL can be decomposed into cells that are compatible with these sets. So just to remind you, you decompose RL into these pieces called cells, and compatible, it means that every one of these sets is a union of these cells. Okay. So compatible with x1 up to xk, such that, okay, so exists a cellular composition. This is just a general theorem of O-minimality, but we want to say something about the number of the cells. So the number of the cells is going to be polynomial in K and D. Okay, so about this notation, what this means is a particular polynomial, okay, that depends on L. So its coefficients and the degree can depend on L, but you plug in K and D into this polynomial. So the number of cells is bounded by a polynomial in L in K and D, does not depend on the particular sets themselves, and Cj has complexity every cell. Okay, every cell has complexity polynomial in D. Okay, and as a corollary, so I mean, I'm keeping the main boards for later, so I will move here. But the corollary will be, from this theorem, is bound on Betti numbers. So it's not a trivial corollary, but it is a corollary. So just in English, sum of Betti numbers of X is bounded by a polynomial in the degree of X, or the complexity of X. So it's not a trivial corollary, but it is a corollary. Out of this effective cellular decomposition, you can construct a simplicial structure for X and bound the Betti numbers. So that's format and degree for the semi-algebraic structure. Note that format actually is just the ambient dimension. Okay, and now Pfaffian structure. So very famous structure, very important structure. And here I will take the time to remind you what I mean. So there is a notion of a Pfaffian chain, okay? So you have B in RL, a box, open, or actually I want it to be closed, but I will talk about that later. So if you have a sequence of functions satisfying a triangular system of differential equations, what does this mean? This means that if you look at the fi function and you look at one of its derivatives, it's going to be a polynomial in x f1 up to fi. So yes, so the first differential equation, it's kind of f1 prime equals some polynomial of x and f1, and then you can add these functions. And the speed depends on I and j. So this is called a Pfaffian chain. And if q is a polynomial in, say, t plus 1 variables, then if you plug into this polynomial, so g will be a function, it's q of, say, no, just t, excuse me, q of f1 up to ft. This is a Pfaffian function. Of degree degree q, but plus the sum of the degrees of Pij. So in the Pfaffian structure, there are many more functions, many transcendental functions, but they all are coming from a algebraic differential system of equations. And so there is some kind of degree input, right? You start with something algebraic, then you have a notion of complexity, and now, so the first thing you do is that one defines format and degree for semi-Pfaffian sets. I will explain in a moment. For semi-Pfaffian sets, just as before, just as for our alg. So what is a semi-Pfaffian set? A semi-Pfaffian set is just like a semi-algebraic set, only these p's and q's are now Pfaffian functions and not polynomials. So very simple concept. And once you have such a set, you define the same thing. The format is the number of variables, and the degree is the sum of the degrees of the Pfaffian functions in this semi-Pfaffian set. Okay, but semi-Pfaffian set is not a nominimal structure. Okay, the projection of a semi-Pfaffian set is not necessarily semi-Pfaffian, and the definition. So in order to get a nominimal structure, you have to add all the projections of semi-Pfaffian sets. So the definition goes like this. So let y in R n, I don't know, large, think about it as large n. Okay, maybe I will do it like the Bourbaki want me to do it. X in RL is sub-Pfaffian if there is, I don't want to write exists a set, but if there is a y in Rn, which is semi-Pfaffian, such that the projection from Rn to RL of y equals x. And the important thing this is not so visible. So, okay, I hoped not to use the board yet, but I must. Okay, and the format / degree of X are equal to the format / degree of Y. Okay, so now we have this structure of this Pfaffian structure or minimal structure. We have format and degree. The next step would be to have some kind of effective cellular decomposition theorem. Yes?
How is format and degree well defined?
Okay, excellent question, and I've been asked to repeat every single question. Why is, because for the recording, so why is the format and degree are well defined? Excellent question. They are not well defined in the sense that they are not unique. You should think about it more as a filtration, in the sense that if you have complexity 100, then you also have complexity 1000. Okay, that's how you should think about it. For the semi-algebraic case, you can be a little bit tricky, because format is always just L. You can try to say the complexity will be the complexity of the minimal possible complexity among all representations. But that's difficult. I mean, that's not for us. That's not what we are interested in. But excellent question. Good, but it's not easy to, a lot of people try to have such a theorem for the semi-Pfaffian structure, and it's not so easy. But there is now a theorem by Benyamini and Vorobyov which kind of solves this issue. And please bear with me because it's weird. The way it's stated, it's weird, but it's worthwhile. So, sub-Pfaffian sets can be endowed with two natural numbers, So they already have two natural numbers, right? Format and degree. But there are additional to natural numbers called star format and star degree. Such that. So the first part of the theorem is that if X has format F, if X has format F and degree D, then it has a star format OF of 1, star degree, poly FD. So, if you have a sub-Pfaffian set of some format and degree, it will have larger star format and star degree. But the bound on the star format does not depend on the set X, right? Only on the format of the set X. So that's the first thing. And the second thing is that with respect to the star format and star degree, there is a cellular decomposition theorem. So now X, I will write it actually explicitly. Xk in our L sub-Pfaffian. But now of star format F and star degree D. Star degree D. So every one of these sets have star format F and star degree D. Then there exists, but not like this, there exists a cellular decomposition again. Compatible with these sets. X1 up to xk, such that, again, kind of such that. If this was written in a paper, I would probably get some kind of remark about grammar, but okay. Such that, what? First of all, so yeah, is there a question, my dear friends and colleagues?
Maybe I'll wait until we
Good, that's a good idea.
What's the relation of CI and SJ?
Okay, so I will repeat the question. The question about this theorem is what is the relation between Ci and xj? And the relation is that these cells are compatible with x1 up to xk. So I will try to draw a picture, but I'm not good at it. But okay, so the point is that, okay, I know how to do it. First I draw the cellular decomposition and then I invent the sets. So you have some kind of cellular decomposition of RL, so every one of these elements is a cell. Yes, every one of these elements is a cell. And now the compatible means that every single one of these xi's is a union of these cells. Yeah, so the idea that you have some sets in RL and you decompose all of RL into these cells, but every one of your initial sets is a union of such cells. Excellent. So back to the theorem. We have subpfaffian sets of star format F and star degree D. Then there exists a cellular decomposition with at most poly FD K cells. And the star format and star degree of the cells is bounded. OF of 1 star degree poly of D, and I will stop for questions in just a moment because I want to explain something, a corollary, which is similar to the one before, but there is a new point now. So if X is subpfaffian, not of star format and star degree F and D, just of format F degree D, then, how did I write? Yeah. Sum of Betti numbers is smaller than or equal to poly FD. So, for semi-Pfaffian sets, this was known before Benyamini Vorobyov due to Zell, and the new part is that this is true for sub-Pfaffian sets in generality, but notice how in this corollary there is no star format and star degree, and this is the key point. What is the logic of this corollary? You take your set X, it has format F degree D, then it has star format OF of 1 star degree poly FD. Then you use your cellular decomposition. The cells, you cannot say that they have good format and good degree. Only good star format and good star degree. But the number of cells is still bounded. And recall that if X, and recall this. So kind of, the point of this reduction to star format and star degree is that for quantitative applications, you forget about star format and star degree. Kind of, you use it for the cellular decomposition, but then the quantitative applications can be stated without them. Yes, now is a good time for intermediate questions. Good. OF of 1 is a constant that depends only on F. Is a number that depends only on F, a function of F. So it's like a bound, like O of 1 is bounded by some number, OF of 1 is bounded by some number that depends on F. Yes?
I think I don't understand what passing from format to star format changes. Since, I mean, you're just replacing some number by another number, but...
Yes, so I did not explain how they are defined, the star format and star degree. So that will...
But I mean, wouldn't the same theorem just be true if you replace star format by format?
This theorem?
The 1, 2, yes.
Yeah, so it's unknown. It's an open problem.
I have the feeling that it doesn't change the statement.
No, because look at this. If you have format F, okay, good question. If you have format F and degree D, then you have good star format and good star degree. But it's not true the other way around. If you have star format F and star degree D, you can't say anything about your original format and degree. And so these cells, they only have bounded star format and star degree.
Oh, I see.
Yeah. Okay, excellent question.
The other way around. The star format could be a lower number than the...
It's larger, the star format. it doesn't work like that. It's a filtration. It's kind of how much do you need to pay to go from format to star format. Not too much, but to go from star format to format, you have to pay more. I saw some.
That was exactly my question.
Okay, that's good. You and yours too. That's quite a combination.
For the corollary, you need the not bound on n, but do you also need the bound on the star format of the cells?
No.
No.
Yeah. Well, I'm not sure. No, I think just n is enough. Okay, good. Yes, of course.
Is there some restricted? Are they restricted functions?
Oh, excellent question. Yeah. I forgot to say this theorem is for restricted Pfaffian functions. Yes, thank you. For restricted Pfaffian struct. I was about to talk about that later. So, Gal told me about 5 times that the proof will work for unrestricted Pfaffian structures, but he also told me 3 times that I should not take everything he says too seriously. So it's not a good ratio. So, I mean, if he told me maybe 10 times that he knows that it's true for unrestricted, then I would be comfortable saying this. Okay, so this is our introduction, and the rest of the talk is going to be about trying to axiomatize these notions for ominimal structures. Let me check my notebook that I'm not missing anything. Good. So definition. Okay. So fix an ominimal structure. Try to catch it. S. So S for me is just the collection of definable sets in all of our K for every K. Okay. So definition. An FD filtration so it's a collection of omega FDs for any 2 pair of natural numbers. Of course, 0 is not a natural number. So omega FD, right? It's a collection of definable sets, but not necessarily in the same ambient dimension. It's just a collection of definable sets. It's a double filtration, right? So if you have format f in degree d, then you also have format f plus 1, and you also have degree f plus 1. So, yeah. And the last axiom, and of course, if x is definable, then there exists format and degree. So it's a kind of complete filtration. Okay, that's an FD filtration, and just some notation, right? If f is a definable map, so saying that f has format f and degree d, I just mean, excuse me for this, just means that the graph of f. One second, I will address this. So excuse me. No, this f is squiggly. This is the first thing, and the second point is that it's a definable map. So I like capital F for maps and small f for functions. But okay. and yet, it is the correct approach. Good. And another definition. What does it mean for 2 filtrations? So there is a partial order on filtrations. This is called omega 1 is reducible to omega 2. And so I will write down, first of all, using, okay. So what this means basically is that if you have a set which has format f and d with respect to omega 1, then it has a format OF of 1 poly FD with respect to omega 2, but since I've already been asked this question, this one time I will explain more precisely what I mean. What this means is that there is a function a from n to n, and then a function b from n to polynomials with natural coefficients in one variable, such that, now I can write this precisely, omega 1 fd is a subset of omega 2 a of f, b of f evaluated at d. So this is called reduction, and the idea is that, it's like this, it's like the star format and star degree. We had this original format degree, and star format star degree is basically another filtration, and the original format degree is reducible to the star format and star degree. In this sense, it's exactly what I've written there. Okay, and good. And omega 1, if they are reducible to each other, we say that they are equivalent. Okay, so now I have to delete some. No. Go up. Good. I can continue here. Okay, so this is just the notion of an FD filtration, just what we mean by a format and degree for definable sets. Now, for the actual axioms. So definition, and I have about 21 minutes. Okay, I see. So the definition is going to be S omega is sharply minimal. So it's denoted sharply minimal if, okay, so first of all, if you have a set X in R, which is also in omega fd, then the first axiom, which is the most important axiom, is that X has at most poly fd components. So this is similar to the axiom of hominimality that every definable set in R is finitely many points and intervals. Now we want to say to control their amount in terms of the format and degree. The second axiom, the least important one, but my favorite, is that if X is in RL and X is in omega fd, then the format must be at least L. This is because some of the O-minimal operations, they will use the number of variables of the set. Kind of without this, everything breaks apart. It's a regularity axiom. It's the least important one. But without this, everything is false. Okay, now if X is in RL and X is in omega fd, now we consider in the third axiom the unary operations. So the complement and the projection to L minus 1 of X are in omega fd also. And but R times X and X times R, this already increases the format plus 1 by 1. I will before I comment on any axiom, I will continue until the end. So next axiom is that if you have a collection of sets in RL such that Xj is in omega fj dj, and F is defined to be the maximum among these formats, and D is defined to be the sum of these formats, then the fourth and fifth axiom are as follows. So their union is inside the omega fd. But okay, it's in our preprint it's split into two axioms, but no need here. And also the intersection is in omega fd. And the absolute last axiom here, it's about relation to the semi-algebraic structure. So if P is a polynomial in L variables, then its zero set, so it's a subset, it's a semi-algebraic subset over L, it's going to be, it's going to have format L and degree P. Okay, so these are the axioms. Before I make any comments, do you have any questions about one of the axioms? Okay, good. My comment now is that these axioms have been recalibrated several times. If you've heard about Sharpe minimal structures before, you probably saw different axioms. And in these different axioms, the key difference was that certain operations, okay, instead of thinking of a set of axioms where only adding a variable increases the format, initially we thought about axioms where every single operation would increase the format. Something like this. And then there was this kind of saying that the degree is something like the algebraic degree, and the format is something like the depth of if you construct a set using the Sharpe minimal axioms, it's something like the depth of the tree of construction or whatever. But now we know that this is not really true, and the format has a much smaller role, basically only to keep track of the number of variables. Okay, this is the only role of format now. Of course, like in the Pfaffian situation, initially your format is not the number of variables because you are a projection of a set from high dimension. But basically there is no other role for format. Good. So these are the axioms. Okay, I will continue here. Yes, so now I will talk about examples. Yeah, so the question was to give an example, and now I will give an example.
Excuse me.
Yes?
Don't you need something about the polynomial inequality?
No, because, for example, you can say that the polynomial inequality, like p larger than 0, it's like exists y, p equals y squared, for example, and this already you can do arrange with all of the rest of the axioms. But, so yeah, this axiom could have been said that if you have a semi-algebraic set, then its format and degree is just like in the semi-algebraic case. Yeah. Okay, so examples. Okay, so the first example is on the board. It's the R-alg, but not the format and degree that I defined before. Rather, the format and degree that I defined before gives you an FD filtration that is equivalent to a sharp filtration. Okay, but basically that's a little bit technical, not so interesting. The point is that this is sharply minimal, but then also our Pfaff, restricted Pfaffian functions, and of course conjecturally just Pfaffian functions. And to show that R Pfaff is sharply minimal, it's kind of, you need the result by Benyamini and Vorobyov. So just, I will say that the result of Benyamini and Vorobyov uses a lot of research into Pfaffian structures by also Gabriello, Vorobyov, Zell, et al., lots of things, and basically you are not able to show that it is sharply minimal using this format and degree that I defined there, coming from the chain. For example, you don't know that if you have even a semi-Pfaffian set of format f and degree d, you can't bound the format and degree of its complement. You see, you just can't do it. So the way they prove that this is sharply minimal is that they have the star format, the star degree, they have a sharp cellular decomposition, and then you can get all of these axioms up to equivalence. Because, for example, the way they prove it, now you have these sets x1 up to xk of star format fj, star degree dj. So you take the cellular decomposition, and then the union is just a union of some of these cells. And okay, you will get the star format and star degree satisfies axioms similar to sharp 1 up to sharp 5, and up to equivalence it's actually that. So these are the only known examples.
semi-algebraic case is also not quite trivial, right?
Yes, that's an excellent remark that I should have said really in the beginning, that the theorem about the effective cellular decomposition in the semi-algebraic structure, it's not so trivial, yes. But I will explain why it's not so trivial in the generality of sharply or minimal structures anyway.
But to show that semi-algebra is sharp or minimal, it was with the same detail.
Yes. You also have to get the cellular decomposition. How do you even prove that something is O-minimal? Usually you construct cells, right? But then the theory is so that if you have the axioms, then you can construct the cells. So in this sense, it's similar. Non-example. So a very interesting non-example is R-an, the restricted analytic structure. Yeah, so I think you can ask me questions and I can try to answer. All right, let's consider the following function. So it's a strange function. So it's a power series set to the power 2 to the power j. It's called, but it has many gaps in the powers, right? So the next power that you have is just, anyway, you understand what is written on the board. And I claim that this function on the disk of, so it has radius of convergence 1, so let's look at the restricted to a disk of radius 2. It's a complex function, and yesterday in Adele's talk, Adele explained what it means for a complex holomorphic function to be definable, right? So this is what it means. A complex holomorphic function, its real part and imaginary part are definable analytic functions. And suppose that it has some kind of degree. Suppose there is some kind of filtration, there is some kind of omega, and f will have a degree f and degree d. So maybe you can look at the minimal or minimal structure containing f and assume there is omega there, or you can assume that there exists an omega on all of Rn. Doesn't matter for the point that I'm trying to make here. So if you can do this, we will now look at the following equation. Consider the following equation. F of z equals z1. Okay, j equals 0, 2 to the power 0 is 1. So z plus z to the power 2 to the power n plus epsilon n. Let's consider this equation. So f has some constant format and degree. And this is just a polynomial of degree 2 to the power n. So this set, let's look at this as a set. So this set is of format just O of 1, no f this time because I'm not moving the format of f, it's just some kind of constant format. And it has degree a polynomial in 2 to the power n. So really it has degree that the polynomial depending on the format of f in 2 to the power n, comma, the degree of f, but these are fixed. Okay. On the one hand, and thus, okay, wait, before this, but now, if epsilon n is small, what equation we see here? We basically see the equation epsilon n equals 2 to the power, z to the power 2 to the power n plus 1, plus etc., etc., etc. So near 0, you will see 2 to the power n plus 1 solutions, correct? So for if epsilon n is small, this has at least 2 to the power n plus 1 solutions in d of half, if epsilon n is small. So kind of, now I will draw the picture in red. You have the disk, you have some set, of format O of 1, degree poly 2 of n, and you know that its cardinality is at least 2 to the power n plus 1. So you can choose a line and a one-to-one projection between the set and the line. And so, kind of, what I'm trying to explain to you is why I can use the first axiom, even though the set is not really a subset of R, it's a subset of the disk, but what I will do, I'll just project in a one-to-one way so that I will not lose any cardinality. So because now, but by sharp 1, this set, this equation, has at most polynomially in the degree connected components. So I can just write poly 2 to the power n connected components. And instead of writing contradiction, I'm writing dot, dot, dot. We'll let you figure it out. But what I mean is that, of course, you see that 2 to the power n plus 1 for large n is more than a polynomial in 2 to the power n. So it's a weird example. Okay, yes?
Okay, I'm still bothered about the semi-algebraic thing. Right?
Yes.
Sharp 3 seems to, in particular, say that if you take the projection, and so if you eliminate the quantifier,
yeah,
the degree doesn't go. I mean,
correct.
But I thought there were examples where
so the
double exponential, whatever, you know,
no. So it's equivalent to a sharp filtration. About the double explanation, I'm not sure. The thing is that, okay, if you use just general, I don't know, elimination theory or resultants or stuff like this, then you will have very bad bound for the degree of the projection of a semi-algebraic set. But actually, but you know what? If I will ask to return to this point in a few moments, because just now I'm about to say something connected. Okay, so we see that large structures are not sharply ominimal. Also, you can see from this lacunary structure that it's not a solution to a nice differential equation, because if it is, you can try to figure out that it can have so many zeros. Okay, and let's continue. So my goal is to explain how in this setting we can get a sharp cellular decomposition theorem. But before that, I simply must say, I think I simply must say, wait, do I know how to count? I have 45 minutes? So everyone who told me to talk slow, it's not good. It wasn't a good decision. No, but okay.
It was perfect.
Okay, so I have to do the following thing. What we can and can't do. So what we can do from these axioms is, for example, you can get bound on connected components of x in Rl. So the axiom only says that if x is in R, then it has a bounded number of connected components. Using the axioms, we can also prove it for arbitrary ambient dimension. But if we didn't know how to do it, then it would become an axiom. So this is maybe less impressive. But what is impressive is like sharp, not impressive, but okay, sharp definable choice. So you have some definable map. What is definable choice? Definable choice says that one of the possible formulations is that if you have a surjective map, there exists a definable surjective map, then there exists a definable section. So this will be similar. You have a surjective definable map of format f in degree d. There will exist a definable section of format OF of 1 in degree poly FD. And sharp stratification. So if you have a set, you can control the number of strata it has. And okay, this is what we can do. But what we can't do is get sharp cellular decomposition, which is the main point of this entire idea. And the main problem is the same problem for the semi-algebraic structure and for the Pfaffian structure, and it's like this. Say even, I give you, so it's if you follow the proof of cellular decomposition from Van der Drie's book, Tame Geometry, you will get cells, but they will not have good format and degree. And the basic difficulty is universal, a classical difficulty in this situation. Say I give you an equation. I don't know, a Pfaffian equation, format F and degree D, doesn't matter. And say, I even told you that the solutions of this equation over a cylinder are perfectly already ready for cellular decomposition. So the solutions has D distinct roots. Some of these roots are simple, some of these roots kind of oscillate near each other. It's important, it's part of the difficulty. So you can already see the cells. But how do you bound their format and degree? How do you say that so there are approximately D cells, right? Because it's an equation of degree D. How would you bound the format and degree of the middle cell? You would have to say something like, this is a cell, this is a root that has D over 2 roots before it and D over 2 roots above it and so on. The point is that no matter what you do, you will have to put the degree D into the amount of variables you need, in a sense. So kind of you will have to, maybe if you want y D over 2, you will want this kind of, okay. Yeah, so kind of it's not allowed to consider a set like this, right? Y1 smaller than yd. It's functions of, I don't know, x comma, then the yj of x. I mean f of x, yj equals 0. If you want to look at a set like this in order if you want to order the roots of this equation, you can't. This set has D variables, and thus its format is going to be at least D. And when D enters the format, you've lost. You want all the bounds to be polynomial in D, but yeah. Okay, so this is kind of the main difficulty, and in the semi-algebraic case, we are saved by Tame's lemma, by the idea that we don't have to order these roots. We know that the order of the roots can be defined using some inequalities of the derivatives of the polynomial. It's really, we are saved from this issue. But in general, this seems to be the problem. And in the framework of O minimality, I would say that the problem is this. If X is an omega FD, and X dot is a connected component of X, what is the format and degree of F? Of X dot, X circ. So if we kind of knew a good bound in the format and degree of connected components, then I would say that this middle cell is simply a connected component of this entire picture, and then, okay, and I'm really sorry for going over my time, but I have to tell you what is the main theorem of all of this. So the main theorem is that star format and star degree are meant to force one to be able to take connected components. And once you are able to take connected components with good bound on format and degree, then you have cellular decomposition. So I will just quickly write it down, although it's not hard to follow because everything is here. Now this definition might be a little bit complicated. So X is an omega star FD. So X has star format F and star degree D if what? If X is a union of projections of connected components. Please forget about the projection part. It's really just something technical. But the point is that x alpha is in some kind, x is in RL, x alpha is in some Rn, x alpha has format f alpha d alpha, and x circ is alpha in x alpha is a connected component. And so if x is like this, then its star format and star degree, it's going to be maximum over f alpha. And so starting with the sharply minimal structure, you can always create this new filtration. And kind of clearly, you have this reduction. Because if you have a set, it is a union of its own connected components. And the number of connected components is bounded. And this is why we have this one direction. And I hope I did not. OK, good. And the theorem, it's just the same theorem like Benyamini and Vorobyov, but for sharply minimal structure. So if we look at the top board on the right, you have x1 up to xk in RL, sets definable in a sharply minimal structure of star format f star degree d. And exactly the same thing. OK, so what this means, and again, also because of the quantitative thing, what it means is that even if we can't prove sharp cellular decomposition in general, for quantitative applications, the sharply minimal framework is ready, OK? Kind of, yeah. Good, OK. Yeah, I'm done.
According to Benyamini, the motivation for all this was the arithmetic applications like Wilke, counting of rational points. Could you please comment on that?
Yes, I can. I don't know if I want, but I will. OK, yes. So I would say that the sharply minimal framework is convenient for the Pila-Wilke problem, but I wouldn't really say that it solved it. But the main idea in the, for example, Wilke's conjecture is something a little bit different. But certainly, I think this is an important question, generally. I mean, Pila-Wilke theorem is, especially if it's kind of the treasure of all minimality, kind of everything. It's very important, so this is why I do feel like I want to address this question. So the general theorem is that if x is, it has format f and degree d, then the general theorem will say that for every epsilon larger than 0, the number of points, if x is in RL, the number of points that are in the transcendental part of x, which also, and all of whose entries are rational, and the height of these entries. So if you don't know, height of a rational number is the maximum between the numerator and denominator in absolute value. So the general theorem says this. So yes. So the general Pila-Wilke theorem for the sharply minimal framework, it looks almost like the original one. The only difference is the constant now no longer depends on the geometry of x. The constant no longer depends on the geometry of x. But it's not a huge improvement, although it is something. And it's been written in several places, but there is no proof anywhere. But I will say that there is a theorem like that in a work by Benyamini, Jones, Schmidt, and Thomas, just this theorem for restricted subfacial structure. And the same proof will work in the general...
Where is epsilon?
Here? Where is epsilon where?
No, in the set.
Okay, so it's a good question. The point is that the growth, you don't know exactly what it is, but it is sub-polynomial. So for every epsilon, the growth is slower than h to the power epsilon. Yeah. No, it's an excellent question. But, okay, now a very important definition. Yes, it's a good question. So basically, Pila-Wilke theorem is about counting points on a set. And if you have a set, it can have maybe some kind of a transcendental part and an algebraic part. And this is a circle, this is non-algebraic, let's say. And the question of finding rational points on algebraic sets and on who asked me this question? Sorry, so that I can. Yes. And okay, so looking for rational points. Excuse me?
So this means the transcendental part.
Yes. Okay, yeah. It means the transcendental part. Never mind the correct definition. The point is that you take all the algebraic pieces and remove them because it's a different problem. Now the definition here is that S omega have, and this is now not just a kind of axiomatic definition that is boring. This is a key mathematical definition. Sharp derivatives. If you have a function of format f in degree d, then its rth derivative, wherever defined, will have format still f, or f of 1, and degree polynomial in R and D. And this is the key definition that explains, that allows you to get a better asymptotic here. And now the theorem, is that, yes, so if S omega has sharp derivatives, then this kind of the subpolynomial growth, this set is denoted Q of X TR. Yeah, I mean, I wrote it one. So it's smaller than polynomial f d h, excuse me. Yeah, there is an h here, log h. And kind of, this is the key property that allows you this far better thing. And so it's convenient to talk about these things in the sharply minimal framework. And I will say that this problem, this sharp derivatives, is similar to the problem that I talked about before. So if you have a function and you want to define the rth derivative using a formula, you will have to introduce at least r new variables, if you think about it. You will have to have a variable for the first derivative, then to say that the next that this is differentiable, and so on. And once you have kind of r variables, r is not entering the degree, it's entering the format. In the Subpfaffian structure, we can prove this by hand because f is a solution to a differential algebraic equation, so its derivative can be expressed algebraically using the functions themselves. Okay, so yeah, it's a very important question, so this is why the answer is a little bit longer. Yeah.
So easy question. This, so you wrote that this omega is, well, less or equal omega star. Are they actually equivalent?
Okay, so no, this is like an open question. So if they were equivalent, so kind of, if you have this, then it means that S omega has sharp cellular decomposition. So I did not define, but when I say sharp cellular decomposition, I mean exactly like Benjaminian-Vorobyov's theorem. And this is because we have a theorem that with omega star there is a sharp cellular decomposition. So I don't know if they are equivalent, but it's basically, to say that they're equivalent is the same thing as to say that every sharply minimal structure has sharp cellular decomposition, and I don't know. Yeah, and I mean, and this question, if they're equivalent, it's like saying that you can bound the format and degree of connected component. This is a question that I think a lot of people thought about for a long time in the Pfaffian setting, and there is no answer.
So is there anything like, if you start with the Shapley minimal structure and you take the Pfaffian closure, then you remain Shapley minimal?
Okay, so almost. I mean, Bignamini has this new notion of log Noetherian functions, and there is we conjecture that it's a no-minimal structure. A Sharp minimal structure, excuse me. And then, I mean, you can add any solution to a differential equation that you want and remain sharply minimal. But right now, we don't have such theorems. But I will say that since there are only 2 examples, we need more examples. But yeah, okay. By the way, I have to. It's like the joke in The Office, right? So this one I can't, right? It's. So, yeah.
Okay, let's thank the speaker again.
Thank you.